Yeah. Hello everyone. We, the members of Astro Club of Ferguson College, welcome you all to our online lecture on the search of new physics. And our speaker for the day is Dr. Nishita Desai. She has done a PhD in elementary particle physics at Harishchandra Research Institute. She has been a postdoctoral researcher at University of Heidelberg as well as CNRS. Currently, she is a Ramanujan Fellow at Tata Institute of Fundamental Research, that is TIFR, Mumbai. She is a particle physicist interested in studying physics beyond the standard model. Her expertise lies in performing detailed simulations of collisions events to determine prediction of new theories for experiments. We are all really grateful to have you here today, and we all welcome you.
Thank you, Surbi. Okay. So thank you very much, all of you, for the invitation to come here and talk to you. It's always a real pleasure to talk to people from the Astro Club of Ferguson College, and I was once a member of the Astro Club as well. So today I'm going to tell you a little bit about the search for new physics, especially in the sense of new elementary particles. So let's start. But before we get into the main talk, I would like to say to everybody that please ask me questions anytime. And especially if you don't understand why, if you don't understand something that I said, or if it contradicts your intuition, please ask me a question. And you can see at the bottom right of my slide, there is a pause written. So I have these pauses all throughout the slides. And what I will do when I come to a pause slide is to pause and ask you a question. You can ask me questions, I mean. The only thing is that currently, since we are broadcasting this on YouTube, there might be a lag. So I would suggest that you just ask your questions whenever you can. And then when we pause, I can just take them at that time, okay? So don't wait to ask me when I pause. Just type it whenever you think of a question. Okay, let's go on. So the first question you should ask as soon as you see my title is, why do we need new physics? Why should it be there at all? Okay, so that's the first part of the talk. And an obvious answer for that is are the words dark matter, which have become very, very popular also in the newspapers lately. And I'm very glad to see that the previous lectures of Astro Club have covered cosmology and gravitation in such great detail. So you guys already know a little bit about what I mean when I say dark matter. So here is a schematic diagram of one of the observations that tells us that there is more out there than what we already know. So this is a sort of a plot which is overlaid on the picture of a galaxy, and what the plot shows on the x-axis is the distance from the center of the galaxy, and on the y-axis you have the velocity of the stars. Okay, and you would expect, just if you assume that the mass of the galaxy is proportional to the light that you see, that you would assume that the speed of the stars as you go further from the center eventually will drop off. Okay, so that's the dashed curve you see. However, if you actually make observations, that is not what you see at all. What you see is the solid curve with the observations shown here, and which sort of seems to contradict our intuition, because we know that if something is moving faster than the escape velocity, then it cannot be gravitationally bound anymore. So the only way, or rather one obvious way to explain this, is to say that there is more matter in the galaxy than what we can see, than what is visible, than what is incandescent in these stars. So that is a very nice, obvious, by obvious I mean a very visible example. The next example I show you is of this galaxy cluster, which is also very, very famous, and it's called the bullet cluster because you can see that the image looks a little bit like a bullet passing through a gas. And what this image, it's a composite of two things. And what you see in the pink blobs is the actual visible matter. And then the blue blobs are reconstructed based on the bending of light from the galaxies that are behind it. Okay. And what this picture tells you is that all of the real matter is actually in the blue blobs, which you don't see, which is not visible. So this is again conclusive proof that there is some kind of invisible matter out there, uh, which is capable of, I mean, which is really massive, okay, and is probably more than what we can see. So that is what we call dark matter. And I would like to stress here, because it gets lost sometimes, that dark means invisible, not black. So it's not something that absorbs light and it's black, but it is something through which light passes without interaction. Okay. Okay. So what do we know about this kind of matter? So first of all, we know that there is about 5 times more matter in the universe than what we see in stars and galaxies. This new kind of matter does not interact very strongly with our ordinary matter. So in this picture that I showed you, you can see that the dark matter blobs are actually moved farther apart. So it was a collision between two galaxy clusters, and the dark matter is actually moved much farther apart. So interacts much less than normal matter, which you see in the pink blob, which is still close together because it's still interacting. Okay. Then we know it's not electrically charged. Why do we know that? That's because everything that's electrically charged interacts with light. Okay. So if it doesn't interact with light, it cannot be electrically charged. And we know that it is slow moving, and I mean this in the sense of it's not relativistic. Okay. And therefore it should have some mass. So I don't know whether you guys have done relativity before, but the idea is that if something is massless, like the light particle photon, then it always moves at the speed of light. It cannot slow down. So if it is slow moving, then it has to be non-relativistic. So that's the last thing that so whatever this dark matter is has to have these properties. Okay. So then we can ask further questions. Is there a particle that corresponds to this dark matter? If there is a particle, is there one or are there many? So for example, the matter that we know of, that you and I are made of, has many things, right? You have protons and neutrons and electrons that form atoms. Atoms interact and form compounds. Many compounds form the biological structures that we are. So is it a complicated sector, or is this just a very simple sector with one particle? We don't know. We don't know, does it interact at all with ordinary matter? Or maybe we just know that know of it gravitationally because it shows us some gravitational signatures. So we don't know that. And if there is a particle, then what are its properties? Of course, we don't know whether it is a particle, so there's no question of us knowing its properties. And finally, even though we might know how much dark matter there is in the universe, that does not tell us a lot about how much dark matter there is in our neighborhood, in the solar system. So if we send out a satellite and decide to measure somehow how much dark matter is there, there is no guarantee that we will see something, because we don't really know how what its structures are. So there are lots of questions to ask, and so this talk is going to answer some of them with certain hypotheses. Okay, so there is a pause here. So if there are any questions already, maybe I can take them. So, Shrutik, are there questions? Yeah, okay. So I saw one. Okay, so someone has a doubt whether dark matter absorbs things. It does. Well, we don't know. It for sure does not absorb light. So I don't know what would you mean by absorb things, but yeah. Okay, yeah. Okay, let's go on then. So to understand whether this is something new, first we have to understand what we already know. Okay, so let's start with trying to understand that. So what we already know is called the standard model of particle physics. Okay, so this is what we want to do. So first of all, we want to understand how to systematically look for clues of breakdown of known physics. So even if you know what is known, you need to understand when exactly will you say that we no longer follow what is known, when something is different. So I'll give you a simple overview of our standard model. And then we're going to take a quick look at some of the experiments that are going on that can find this kind of dark matter. So that is what is going to be in this talk. Okay. So I want to give you a definition before we start. And this is a common cause for misunderstanding is when a physicist says, I have a theory. Okay, because when we talk to each other normally outside of science or especially in politics and so on, when we say I have a theory, we mean something that I have something that is unproven, unfounded, and it causes a lot of misunderstanding when communicating science to people. So when a physicist says a theory, it is a precise thing. So it is a mathematical description that can be used to calculate testable predictions. Okay, so you cannot just say, oh, I have a theory that there is some gigantic thing out there. It's just a theory, but you have to make a prediction of what are the consequences of whatever theory that you write down. So remember this. And also physicists use the word model and theory interchangeably. Okay, so when I say the standard model, it is an actual mathematical theory that makes certain predictions. So both of these words mean the same thing. Okay. So the next thing that I want you to remember and understand is that we can have different theories to describe different objects. Okay. So again, this is something that we understand already. So we've learned how to calculate the trajectories of planets or how a ball moves when you throw it in the air. We've been doing this since school. And we don't really need to understand the motion of each electron in an atom to understand how the ball moves, because the Newtonian mechanics that we learned in school is perfectly all right to explain this to a very, very high accuracy. You can send rockets to the moon with just Newtonian mechanics. You don't need anything more. So even though there is quantum mechanics, doesn't mean that you always need to use quantum mechanics. And that is because the behavior of objects of different size can be described by different equations or different theories or different models. Okay. And the thing that I work on in fundamental physics asks the following questions. So it asks what are the building blocks of nature, and it asks if those are really truly the fundamental building blocks or is there something smaller. Okay, so that is the smallest. So we go towards the direction of the smallest objects that we can see in some sense. Okay, so let me just change something here. This is okay. Sorry about that. Yeah. Okay. So this is just a cartoon picture of what we know so far. Okay. So our size is approximately of the order of 1 meter. So I've drawn a zebra here. Okay, so that's our human intuition level. We understand things that are of this size very well. Objects that are bigger than this can also be understood and described very well by what we call deterministic physics or classical physics, which means that if you give certain initial conditions and you write down the equations of how these things will move or behave, then you can predict whatever happens at the end very, very accurately. As you become small, as you go smaller and smaller, so things become a bit more chaotic, and eventually you have to go into the probabilistic regime or the quantum regime, okay, where you can't make predictions about an individual particle or an individual atom, but you can make certain probabilistic statements. And on this blue to red band, you can see are the different length scales of the objects that I was just talking about. So we are at about 1 meter. For about 10 to the minus 6 level, you can observe things still with a microscope. So that's a micron. And as you go smaller and smaller, obviously these things are insufficient. And what you can see in this small black picture there with certain lines coming out is a picture of a collision that is happening at the Large Hadron Collider machine in Geneva. Okay, so what this is telling you is that to look at very, very small distances, what you need to do is you need to build new kinds of experiments because microscopes are clearly not enough. Okay, so again, I can also go through some the forces that are important at different scales. So as we know, for very large objects, the force that is the most important is gravitation. For objects of everyday scale, the most important force that governs is electromagnetism. So why do I say that? There is a reason why I don't fall through the chair, and that's because the electrons in my body repel the electrons in the chair, right? So that gives a force, which means that I will not fall through. So for our everyday objects, the thing that governs us is electromagnetism. The way DNA folds, everything is governed by electromagnetism. As you go to smaller and smaller to nuclear sizes, to the small nucleus sizes, the forces that govern you change. And again, so we've learned these four names. There are four kinds of forces: gravitation, electromagnetic, strong, and weak nuclear forces. So this is just a scheme of how they behave. So I think there are some questions. So let me take that. What makes dark matter different from normal matter? Okay, so I told you what makes it different from normal matter. So first of all, it doesn't really interact with light, so you can't really see it at all. And I mean, that's basically it. And it's the question that we should ask: what makes it different than normal matter? So the answer is we really don't know what makes it different. We don't know why we can't see it. That, in fact, is one of the questions of particle physics. Okay, so we can go forward. Okay, so this is sort of a history and an overview of the different kind of forces that we have. And I want to tell you a little bit about how we arrived where we are today. Okay, so this is, we start from the things that we learned in school. So the periodic table was made in the 1860s, and people realized that each element that we see has a certain atomic number, which remains unchanged in chemical reactions. And in the 1890s, some people discovered radioactivity, which means that one element can transform into the other. So even though first we believe that each element is unchanged, now we have radioactivity by which you can change one element into another. In the 1890s, again, the electron was discovered for the first time, and it was found that it is not possible to have a smaller charge than that. So it was given a charge of unity, and just by the convention of what was called positive and negative charge at the time, the electron turned out to have a negative charge, so it was given a charge of -1. Okay. It was also understood that in radioactivity, what was called beta particles are actually electrons. Okay, and during this whole radioactivity boom, radioactivity studying boom, one particular scientist called Rutherford started making a lot of experiments where he threw one kind of radioactive particles towards a very small thin sheet of different kinds of metals, so in particular of gold. And I guess most of you have studied this already. And by noting how this incident particle comes out on the other side, he made certain important conclusions. Okay, so the first conclusion that he made was that the nucleus was a positive charge and that was surrounded by some kind of negative electron charge. And now we know that the minimum nucleus is the proton. Okay, but the most important thing is that this technique for seeing that was developed by Rutherford is used today as well. So the nucleus of an atom is much, much smaller than any visible light that we can see, right? And so how do you see this is by throwing much smaller things towards the big thing that you want to see. Okay, so this is something that we still do, and I will tell you a little bit more about how we do it now. Okay, so but before we go there, there are certain basic fundamental laws that we need to understand and remember. So the first is conservation of energy and momentum. Okay, so whenever you want two things to collide, so remember you're going to try to see objects by throwing other objects at them. So you're colliding objects, and you have to remember always that the incoming momentum of objects will be equal to the outgoing momentum of the objects. And similarly, the incoming energy of the objects will be equal to the outgoing energy of objects. So this is a very powerful statement. Let's just make a lot of predictions. Okay. So that's the first thing. The next thing that I want to introduce to you is this idea of scattering. So it's the same thing that can be viewed into two different what we call frames. So the left-hand side picture is something that is very familiar, where you have a stationary object and you hit it with something else. And so normally if it is like a billiard ball, then both of these will move away. But of course, since we're talking about looking inside fundamental objects like nucleus, so if you're breaking apart a nucleus, what will happen is that this thing will break into two and you will have two different things flying away. There is another way of looking at this exact same process in a different what we call reference frame. So this is something like if there's a moving train and if you ride a bicycle as fast as the moving train, the train is going to look stationary. So that's a different reference frame that you have. So you have one frame where you are stationary and the train is moving, and another frame when you're moving at the same velocity as the train and the train appears stationary. So this is just what I mean by reference frames. So you can just change your reference frame, and now this collision looks like two particles are coming from the opposite side, and then the split nucleus, for example, is moving again from the center. Okay, and this is a very particularly useful reference frame to have because of certain nice properties, which is that the momentum is always going to cancel. So you have this nice balance of momentum always. Okay, so what else can we understand from scattering? Okay, so again, let's go back to our billiard ball example. So we want to understand the billiard ball by throwing other small objects like marbles at it. So if you throw marbles at it, how many marbles will be deflected by the billiard ball? So there's a very easy, intuitive understanding of this. And that is simply the area of the billiard ball, right? If the marble falls inside the area, it will be deflected. If it falls outside the area, it will not be deflected. And this area is basically just what is called a cross section, which just means you cut this billiard ball in half and look at what the area is, then that is going to be pi r square, where r is the radius. So that's the cross section. But now assume that the billiard ball is positively charged and the marble coming is also positively charged, then it doesn't actually have to hit the billiard ball to feel its effect, right? Because we know positive charge is repelled. So it can come a little bit further off. So even if it comes like this, it will still be deflected. So measuring these kind of scatterings is very useful because it also tells us a little bit more about the charge of the objects that you're studying, okay? And so what particle physicists do is that they measure this cross section, or rather they measure how this deflection occurs when you throw different things at this guy, and use that to make certain inferences about the mass, the charge, and so on of the objects. Okay, so then we can go ahead. So something special happens some of the times in particle physics that is completely non-intuitive from billiard balls, okay? And which is that you can produce a whole new particle. So remember 2 slides back, I showed you this picture where you have the total energy available is the sum of the energy of the incoming particles. And sometimes what happens is that this energy is just right so that you can actually produce a whole new particle. So this never happens in billiard balls. You can't hit 2 billiard balls and suddenly make, I don't know, a tomato or something. But in particle physics, it can happen. And you can think of it intuitively. This is not the right physics explanation, but as a metaphor, as an intuition, you can think of it as hitting just the right frequency such that you are producing that particular particle, okay? And this is what particle physicists call a resonance. So when particle physicists talk about discovering a new particle, most often what they mean is that they want to discover a resonance in the cross section. Okay, so there are some questions I see. So let me try and take them again. I'm sorry I have to come out because my mouse disappears whenever I'm sharing the screen. Okay. So the first question is, by the definition of theories, do we have dark matter theories? Yes, there are many, many dark matter theories out there. And in fact, I will show you at the end of the talk how some of them have already been have already been proven wrong. So there are many dark matter theories out there. There is not just one theory. Then we have a question: does dark matter scatter or reflect or refract light as it doesn't absorb it? So no. So when I say that it does not interact with light at all, it automatically means it does not scatter or reflect light. About refracting light, the question is more complicated, because refraction, usually when we talk about it in everyday sense, we talk about it when light passes through a medium, right? So when light passes from air to glass, it refracts because the speed of light in air is different from the speed of light in glass. So it doesn't refract in that sense, but I can understand that you might be confused, because I showed you this picture of the bullet cluster where I told you that light bends, and that's how we infer the mass that was there. And the bending is not from refraction, but it is from what is called gravitational lensing. So it bends because gravity bends the space around that particular mass, essentially. And that is what gives an appearance of refraction, but it is not really refraction. Okay, so how are we doing for time? Okay, so I should really hurry up. Okay, so right. So I've given you two important ideas about what scattering is and what a resonance is in scattering. Okay, so let me just give you one more thing. So remember, cross section was an area, right? And then if you hit it with number of particles here per unit area, then you can predict the number of collisions. So this is a very straightforward equation, right? So you have n number of particles that come per unit area, and this is the area of interaction. So that gives you the number of collisions. So how do particle physicists test a theory, right? So each different theory predicts different number of collisions, essentially. And you perform an experiment that counts collisions of a specific type. And then a different theory predicts a different number, and that's how you can distinguish. Okay, so you might have seen this kind of figure a lot in the news. So about 7 years ago now, there was a Nobel Prize given for the discovery of the Higgs boson. So this is a plot, so don't worry about the details of the plot. I just wanted to show you that what I'm talking about is actually real. Okay, so what this plot does is on the y-axis, you have the number of events that have been observed of a certain kind of collision. What kind of collision? So that's written on the right. So you have two protons and you have two photons or light particles that come out. So that is the kind of collision that they're observing. Two protons, they're giving you two photons. Okay. And you see that there is a smoothly falling observation of how many photons you get from collisions of this kind. And you understand that very well because you can use the standard model, which is a mathematical theory, to calculate the shape of that fall, essentially. And then in the middle, you see suddenly you have just the right energy to produce a new particle. And this is what they measured, and this is what is the Higgs boson. Okay, so this is how the measurement was made. Okay, so that's just what I wanted to show you, that resonance. What do I mean when I say a resonance in scattering cross section? So this is what I mean. Okay, so this is again just written in words what I just said to you. So how do you find new physics? You calculate the cross section based on your theory, and you test whether the observation is what you expect, or you find an unexpected resonance in cross section sometimes. Or sometimes it might happen that you will find violations of fundamental conservation laws. So I'll give you an example of that in a minute. And that violation first is in beta decay. So if you remember, in beta decay, what happens is that a nucleus emits an electron and becomes another nucleus with a higher atomic number, right? So what is happening is a neutron is emitting an electron and turning into a proton. Okay, and people measured the direction that the electron comes out, and so on. And we know now that the proton and neutron both carry spin half, and the electron also carries a spin half. And there is no way to get this reaction properly, because you can't add two vectors of spin half and get a spin half vector. You can either get spin 1 or spin 0. Okay, and so there's a mismatch here. And to explain that, what was done is that an invisible neutral particle of spin half was proposed to carry the missing, this missing angular momentum, and it was called the neutrino. Okay, so so this is the way you test fundamental laws of physics. I mean, so you know that angular momentum has to be conserved, and if it is not conserved, then the only way to explain it is that there must be some new particle there. Okay, so yeah, so then you can obviously ask the question, is the neutron made up of proton and electron plus a neutrino? And the answer is actually no. And it will be a very long journey to see why this is no. So that would have been the obvious answer, excuse me, but that is actually not true. So we are going to go on that journey now. So everything that I told you up to now is already almost 100 years old. So particles known in 1935 were the following. You had the proton, the neutron, the electron, and its antiparticle called the positron, and the neutrino. Okay, and everything that we see, stars, planets, table, me, you, everything, is made from just these. And so at this time, people thought, oh, we finished physics. We understood everything. There's everything beyond this is just, just writing more and more complicated equations for these same kinds of objects. And nature had something else in mind. So obviously, there was the big Second World War in the middle. After the war was over, people started doing physics experiments again. And what they saw, so what people were doing at this time, so photography was developing very fast, and people started taking photographic plates to different places and trying to observe what kind of things you see from the sky and so on. And people started observing charged particles in the atmosphere. Okay, and they saw new kinds of charged particles that had masses between the proton and the electron. So it didn't fit with the proton and it didn't fit with the electron. So they didn't actually know what it was, and they just called it a meson. A meson means something in the middle. And so these mesons were unexplained. And unfortunately, they just became more and more. So people started also colliding protons in smaller scale experiments. So tabletop experiments and so on. And they also started finding these kinds of new particles. So you can see a star, which is essentially the track of every single charged particle. So so you can make certain photographic emulsions, and when a charged particle passes through it, it leaves certain small bubbles. And then if you take a photograph, you can get photographs like this. And you can see those A and B particles that are marked with a zigzag arrow. And you can see that they seem to come from a point, but that point doesn't coincide with the point of collision, which is the big star, right? And so what is happening here, presumably, it looks like that there is an invisible particle that was produced at the star. It traveled a little bit, and then it decayed into two charged particles again. Okay? So again, there were these invisible particles so there's reason why it's not the neutrino, but anyways, there's more invisible particles that are coming out, and you don't know where they're coming from or what they are. So it was a very confusing time. People didn't know what was going on. And all of these new particles that were found, there were hundreds of them. It was found by Murray Gell-Mann that you could fit them into these very nice, what shall we call them? A very nice scheme if you made certain assumptions. Okay, so these mesons and similarly these particles that form these stars, which were called hadrons. So all of these could be understood by assuming that they were made of some other fundamental particle called a quark. So that was his assumption. And each hadron is made up of three quarks. So protons and neutrons are also hadrons. And he proposed three kinds of quarks, which he called up, down, and strange. And up and down are what form the proton and the neutron. And then with this range, he could explain nicely all of the other particles, all of the mesons and hadrons that were discovered up to that time. Okay. And you will remember that I said that the electron charge is -1, and there is nothing smaller than electron charge that can be seen. And that was also true when observing these mesons and hadrons. You could only see +1, -1, +2, -2, and so on. So what do we do about that? So he said that you can only make combinations such that they make up a whole number. Okay, so you remove everything that is not a whole number, and you get this very nice diagram where everything fits. So that was his great idea. And then obviously, if this is true, then we should ask, why don't we see the quarks themselves? And then you have to make another assumption that there must be some kind of very strong force that keeps them confined within mesons and hadrons, such that you only see integral numbers of charge at the end. So there must be some extra strong force. So now by this time, I'm sure you must be thinking this sounds completely nuts. It's completely arbitrary. But here is where the testing phase of a theory comes in. So you can come up with a crazy theory, but if you can test it well enough and you can make very detailed measurements and prove that they are all in line with the theory, you can make predictions, then of course you can prove the theory. So that's what people started to do. So this cartoon figure is from one of the first colliders. Okay, so this is from a collider made in Stanford, which was made to look inside the proton. So if it is indeed made of quarks, then you should be able to see inside it. And the idea was that you have a proton on one side and an electron on the other side, and you hit the proton with the electron and see what comes out. And so they did that. And what you see that comes out is actually not quarks, but you see mesons and hadrons, which sort of proves that you cannot have quarks by themselves, but you have mesons and hadrons. And then you can make certain exquisite measurements that can that essentially measures the charge of each quark. So unfortunately, I will not be able to go into the details of it, though this diagram that I have here is actually explains that. And so I'll just say it in words for those of you who have done some of these studies might understand. So what happens is that an electron emits a photon, which is a light particle, which is absorbed by the quarks in the proton, and it goes further, right? And the interaction of the photon with a particle is always dependent on its charge. So you know the charge of the electron is 1. So whatever the charge of the other guy is going to affect the total cross section. So the total how much interaction happens. So if the charge is 1, you're going to have a large interaction. If the charge is 1/3, you're going to have an interaction that's that much smaller. So you can measure actually how much it interacts, and that will give you the charge of the object that is inside the proton. So that is how they measured the charges of the individual quarks and proved the theory. Okay. But that was not the end of the story. So we found not only quarks, but we found again the same problem that we had with the neutrinos. So you have these kinds of events where now what you're looking at is so there's a collision like this, and you're looking in this plane. Okay. And I told you that there are hadrons and mesons that come out and they form these jets. So you can see three very hard jets here, very clear jets here. And again, if you have E plus, E minus, or E plus and or electron and proton, which are both spin half, there is no way to make 3 quarks because quarks are also spin half. So what is the third particle? And this can only be explained by assuming a new kind of particle, which was named the gluon. And now we know also with more detailed experiments that the gluon is like the photon, like the light particle. It is responsible for mediating strong interactions that keep the quarks together. Okay, so photon is the light particle that mediates electromagnetism, and the gluon is the mediator of the strong force between quarks. The photon has an interacts with particles that have an electric charge. So what is the charge of this strong force? And this charge has been named color. And the reason it is been named color is just out of a very nice metaphorical overlap. So each quark comes in three colors, red, blue, and green. That doesn't mean that there is an actually red colored quark, but it comes in three colors. And you only see, so remember, protons and neutrons have three quarks in them. And you only see objects that are color neutral, that are white. So if you have one red, one green, one blue, then they make white, so it's visible. Similarly, for mesons, you will have a quark and an antiquark. So antiquark come in opposite colors, and you can make a red, anti-red. Anti-red is cyan. So you can make a meson out of that. So it's just a nice way to remember, because colors behave in a very similar way. Okay. So this is just convenient labels, but now we know that there is an extra charge in the universe aside from just the electromagnetic charge. And that is also not the end of the story, because some of the mesons that we discovered out there turned out to be not these things made of quarks, but actually fundamental particles like the electron. So there we found one of the mesons which is now called a muon, which was at that time called the mu meson, is almost exactly like the electron, except it's about 200 times heavier. And then with more experiments, we discovered another cousin of the electron that is called the tau. We found cousins of these neutrinos, and also like the up, down, and strange, we found three more quarks as well. So this is the entire picture of this spin half sector that we have now. So we have 6 quarks and 6 what are called leptons. So leptons do not carry this color charge, this red, blue, green that I was talking about. So that's how they are different. And all of the matter that we know of is formed of these guys, except for dark matter. Dark matter is not formed of these guys. Okay, so let me take some questions. Does dark matter decay like normal matter? Okay, so the question is slightly complicated, because we don't know whether dark matter is one particle or is it multiple particles like nuclei. So if there are dark nuclei, they might decay into other dark nuclei. We don't know. So that is entirely possible, but there is no way for us to see, because both the things are equally dark to us, right? However, if you assume that it is a single particle, then by definition, it cannot decay, because it has to be stable, right? It cannot decay into something else. If it decayed into electrons, for example, then we would see it. If it decayed into protons, we would see it. So in that sense, it depends on what your assumption is for what this dark matter could be. But in general, the simplest theories that we have assume that the dark matter does not decay. Okay. The next question is, what is rest energy of a particle, and can we harness it? We do harness it. Not in a very good way, but that's how atomic bombs are made. So that's how, in a good way, we harness it by making nuclear reactors, right? So when you split a heavier nuclear into 2 lighter nuclei, the excess amount of rest energy that was in there is harnessed as electricity. So that is happening already. Then the next question is there a trend in the amount of dark matter in different types of galaxies? I don't know about a trend. There are definitely different kinds of galaxies. So there are galaxies that are very poor in dark matter, and there are galaxies that have almost no visible stars at all, but are all dark matter. Just almost completely dark matter. In fact, our Milky Way has several smaller satellite galaxies that are almost entirely dark matter, and they are used quite a lot in trying to find what dark matter could be. So I'll come to that in a few slides. Yeah. Okay. So the next question is, does dark matter scatter? I already answered this one, I think, whether it scatters, reflects, or refracts light. Okay, so let's not go there again. Okay, so we can just go to the next slide. Sorry, there's one more question. How do we know dark matter interacts with gravity since we have no evidence of graviton? So the graviton doesn't even come into it so far. We know that this is making things unnecessarily complicated. So we know that it affects, the fact that we can observe, for example, lensing because of dark matter simply means that it distorts space. So that means it has how should we put it? It can be seen gravitationally. That's probably the best way I can put it. You can infer its existence due to gravitational measurements, lensing measurements, for example. The graviton is an unnecessary complication. I know a lot of people like to talk about the graviton and quantum field theories of gravity, but we are very, very far from getting any such theory that is viable. So so let's not talk about the graviton at all. So I told you how we know that the dark matter exists. We know the dark matter exists because we have several observations that say that there is some kind of invisible matter out there and we don't know what that is, and we call that dark matter. So that's about it. Okay. To summarize everything that I've said so far into some very simple things. So we know that there is matter and there is interaction between matter. And the way we explain it now, so the modern theory of particle physics, or the standard model, all matter particles have spin half, and all force particles have integer spin, so 0 or 1. And the integer particles essentially carry forces between two matter particles. So that's our understanding. And the charges that particles have are the electric charge and the color charge. Okay. So is this the end of the story? It's not. And if you remember, I sort of made a half statement saying that the neutron is not made up of proton, electron, and neutrino. And the reason is that the strong force actually does not explain beta decay. Okay, it only explains how there are three quarks inside the proton or neutron. So we still have not understood how beta decay works. And to understand that, we needed a whole new kind of force, which is called the weak force, which connects the strong sector, or rather the color sector, with the lepton sector, the quark sector with the lepton sector. And this is a diagram of how the beta decay actually happens, is that a neutron emits something called, what we now call a W, and a proton, and the W goes into electron and neutrino. Okay, and these Ws were looked for at the CERN collider in the 1980s, and they found it. And there's another companion particle to the W, which is called the Z, which is charge neutral and therefore decays into electron and positron, E plus E minus, and therefore is very nicely seen. So the W, remember, decays into an electron and an invisible guy. So it's kind of hard to see because you will only see the electron, the invisible guy you cannot see. So the Z comes with 2 electrons, and therefore if you actually plot the mass of this E plus E minus pair that comes out, you see this very nice resonance structure again that I talked about. Okay, so if you look at E plus E minus going to hadrons like here, you will see this very nice peak. Okay, so that's how you measure the masses of new particles, by the way. Okay, and then there is this very last bit that is remaining, which has to do with the Higgs boson that I showed you a little bit earlier. Okay, and yeah, so this sounds a bit strange, but this W and Z that I showed you just now are also different from the gluon and photon in that they are not massless. So the gluon and photon have 0 mass, they travel at the speed of light, but these guys are massive. And we don't know theoretically how to write a theory of this consistently. So it will be hard to explain, but unfortunately you have to take my word for it. And the only way to give it mass is by thinking of it in terms of phase transitions like magnets. So you have a phase where the W and Z are massless, and then you have a phase suddenly where they are massive. Okay, And so what happens in magnetism is that you have this unmagnetized phase, all the spins are pointing in all kinds of directions. And then when you have in the magnetized phase, all the spins point in one direction. So that's sort of like giving mass. So in the unmagnetized phase, imagine if you want to move an electron into this unmagnetized phase, you're going to require an equal amount of energy no matter which direction you move in, because all the spins are pointing in all different directions. Whereas in the magnetized phase, if you want to move in the opposite direction to where all the spins are pointing, you're going to require a lot of energy, right? So this kind of requiring a lot of energy to go into one particular direction is sort of, it feels like the object that you're trying to move has become suddenly very much heavier because you're trying to move against something. So you can think of it like this in an intuitive way. So to do this kind of symmetry breaking, where you go from an unmagnetized phase to a magnetized phase, is where you require the Higgs boson. So the Higgs boson, you've heard this many times, that it gives mass to all the particles. And this is the mechanism by which it gives mass. So it gives it causes a certain phase transition such that all particles now start to have mass. And you can actually realize that this is true very well, because you can measure how much this Higgs boson interacts with each kind of particle, and that's exactly what people have been doing. And you would expect that the amount of interaction is proportional to how much mass the particle has. So the first plot on the left I showed you already with the resonance. The second plot on the right is a plot that shows the mass of a particle that is interacting with the Higgs on the x-axis and the amount of interaction on the y-axis. And you can see that there is a straight line going through all of them, which means that the interaction is always proportional to the mass of the particle. And so this is a great triumph of this theory of the Higgs boson that was written down almost 50 years ago, which explains how particles get mass. And understanding the properties of this Higgs boson is going to be a major research agenda over the next few decades. Okay, so now we are at the point where we've seen everything that we know. I'm sorry, we're running a bit late, but this is the whole picture now. We've learned about quarks, we've learned about leptons, and we've learned about kind of gauge bosons. Now we come to the original question that we started with. Okay, so how do you look for dark matter? So there are many, many ways of looking for dark matter, and we have a lot of evidence from the cosmological side. So I showed you galactic rotation curves, and I showed you some lensing. But and I talked about this Milky Way satellite. So I told you that there are some satellites out there which are almost entirely dark matter, and you can actually try to infer their existence. And there are two other ways. One is direct detection, where you have a detector on Earth, and if you're surrounded by dark matter everywhere, as the Earth passes around the sun, you expect that you will pass through this dark matter wind, right? And you try to detect that. So we'll talk about that in a bit, because there's an exciting new result about that announced just 2 days ago. Then there's indirect detection, where what you do is you train your telescopes on these dark matter dense galaxies that I told you about, and you try to see if they interact somehow with matter and you get some light or something. And then the final way, which is my particular specialty, is by colliding two things and trying to produce dark matter in the lab. So that's the way that I look for dark matter. Okay, so there are some questions, so let me take them here. How space-time behaves around dark matter. So as far as we know, it behaves exactly like it behaves around normal matter. I don't think there is anything special. So if you have a huge, massive star, it bends space around it. If you have a huge, massive blob of dark matter, it will also bend space around it. Does higher generation particles appear after doing experiment at higher energies? Yes, because their masses are heavier. So to produce them, you need a lot higher energy, right? Is there a possibility of even higher generation particles? That's a very good question. So you can actually do this experiment, and we've already ruled out the possibility of having higher generation quarks. And that is because of the way the Higgs is produced. So it is, it will be a bit hard to explain. But the way you produce Higgs at the LHC is directly proportional to the number of particles that you have that interact with the Higgs. And so we can put an upper limit based on the observation of how many Higgses we saw. And if there were actually higher number of generations, then you would have seen much more Higgses in the LHC. So you haven't seen that many, so you can see there are only 3 generations. You can also, there are multiple ways to see this, but right now, at least our best understanding is there are not more than 3 generations in the world. Does dark matter have its own standard model of particles as well? It's entirely possible. We don't know anything about it. I mean, yeah, it's entirely possible, but it'll just make it harder to look for, I think. Could you explain whether dark matter are halos and WIMPs or some invisible mass that interacts with gravitational electronic waves? Okay, so there's a lot of buzzwords here. So when you say a halo of dark matter, it's not a particle. A halo simply means that you assume that your galaxy lives in a spherical blob of dark matter. And that's called a halo. So that's an assumption that we make, and it explains our observations very, very well. A WIMP is a particular kind of dark matter particle that theorists have proposed. It could still be a WIMP. We are still testing it, and I'll show you a few ways of testing how if it is a WIMP, how we could detect it. Does not interact with electromagnetic waves at all, because electromagnetic waves is the same as light, which is the same as photon. Whether it interacts with gravitational waves, it will interact with gravitational waves. We don't, well, yeah, you can calculate how it would interact with gravitational waves, actually. Though I don't think we have equipment sensitive enough to see that yet. Or maybe we do. I don't know. We'll have to see. The next question is cosmic rays produced due to interchange of quarks or something else. Cosmic rays are essentially just protons or electrons or things like that coming from outer space that hit our atmosphere. So there is no interchange of quarks and so or something. It's just ordinary particles. We just call them cosmic rays because they come from outside our atmosphere. There might be, I should say that there might be some hidden component to cosmic rays that we haven't fully understood. But then again, we have dark matter detectors and so on that are trying to detect if there is indeed such a component. Why are there 3 different generations of leptons and quarks? What does it mean? Nobody knows what it means. We just know that there are 3 generations, and we can sort of make an argument why there should be at least 3 generations for the universe to be stable. So the answer to that is, again, sorry for the leading answer. So the point is that all laws of physics are generally symmetric. So if you can write laws of physics for matter, you can also write laws of physics for antimatter. And you would have matter and antimatter that would annihilate immediately, and you would just get light. And the reason, the fact that the universe exists, that you and I exist, simply means that there are a lot more protons in the world than there are antiprotons. And we don't understand why that is. Why do you have only matter that is still existing, and what happened to all the antimatter? And one way to explain this is by saying that there is a fundamental asymmetry somewhere, and you can quantify this number. And for this number to remain non-zero, you have to have at least 3 generations. I'm sorry, I won't be able to explain in detail because you need a lot of mathematics for that to come out. But you can't have stable matter without that. So we need at least 3 generations that we know. And there is not a 4th generation that we also know. So that's where we are right now. Could you tell us what the experiments being carried out to detect dark matter? Yes, I'm talking about it right now. Okay, so this was my slide about complementarity of matter. I'm really sorry. We are running very late. Okay. So let me just, this is just saying in words what I talked about so far. We don't know the density of dark matter in the solar system, so let's try to produce it in the lab. And one experiment that is currently running is the Large Hadron Collider experiment in Geneva. So on the left, you have this aerial picture of Switzerland and France, and the red ring essentially is where the underground collider experiment actually is. And you can see on the right what it exactly looks like. So there are 4 different experiments at 4 strategic points. And especially Atlas and CMS are exactly opposite to each other, and they serve a special purpose that they are looking for exactly the same kind of physics. So if one experiment finds it, the other has to as well. So they are a nice cross check, so nobody can cheat. Well, that was a joke, but yeah. All right. So it's also just so that we as physicists can trust our calculations and can trust our observations. Okay. So this is what the control room for this giant machine looks like. So you can see there are lots and lots of screens monitoring lots of different parameters that are needed. And the guy you see, so there's a blue CERN logo, and the guy you see standing below it is the big boss of the accelerator complex. This is one of the detectors or the experiments called CMS. The reason I show you this one is because India is a big part of CMS. In fact, there are no Atlas experimentalists in India, only CMS. And these are some of the pictures I took when I visited the detector. So you can see the components are giant and very, very complicated. In the second picture on the right, you can see one sort of pipe going in the middle. That is the pipe where the collisions actually occur. And this is what it looks like schematically. Okay, so now I've cut the detector vertically, and I'm showing you the slice of the detector. So the collision happens there in the center, and then there are several concentric detectors that are inside this experiment. So the first detector is called a tracker, which essentially shows you the track of every single charged particle. The second one is called the electromagnetic calorimeter. So it stops things like electrons and photons. So you can count their, or rather measure their energy. So calorimeter always measures energy. Then you have the hadron calorimeter, so which stops things like protons and neutrons and measures their energy. And if you have a muon, which I told you was the heavy cousin of the electron, then it actually escapes all of this, and you can detect it outside as well. So you have more tracking modules outside, so you can measure its momentum nicely as it goes out. So the reason this is important is because every other heavy particle, aside from the proton, neutron, electron, muon, and neutrinos, which are invisible, everything else essentially decays into something else. So it's not stable. Okay, so if you can identify these things, then you basically seen everything. So what does an invisible particle look like? So remember, dark matter is invisible. So this is an example of what an invisible particle produced would look like. So remember, I told you we need always we always assume, and this is very, very well tested, that the total momentum is always conserved in a collision, right? And so if you see a mismatch of momentum, then something is wrong. So what the calorimeters do is they basically they measure the momentum and the energy of the particles, right? And you can see in this picture that all of the energy, all of the momentum is only on one side of the detector, and the other side is completely blank. And the only way this can work is if there was an invisible particle, at least one, that went the other way. Okay, so this is an actual measured event. So you can see when the date when it was recorded and the run number and everything. So this is what it would look like. So this is again just in words what I was trying to say. There are certain detectable objects, and all new particles will decay into these known visible particles. And you can use kinematic distributions to define what your signal is. So for example, in this case, your signal is a mismatch of momentum, or what we call missing momentum or missing energy. So these are the words that are used to describe an event like this. And what you would do is you would calculate how much of this missing energy you would see from the standard model alone. And you would count how many number of events you get from the standard model alone, and you count the events that you actually see. And if the number that you actually see is much, much larger than what the standard model predicts, then you can say, I found something. Okay, so yeah, again, so this is exactly what I was just saying. So you count the number of events with large missing momentum, you call that the observation. You calculate how many events neutrinos would give you, which you call the prediction. And if you have observation much bigger than prediction, then you have a detection. Okay, so we have not seen dark matter yet. So far we've seen only what is predicted by the standard model, but we know a lot about what dark matter is not. So what do I mean by that? So if we make a simple theory of dark matter, saying that, dark matter is so and so, and that would mean these many events, for example, at the LHC collisions, but you don't see that many events at all, then you can say this theory is wrong. Okay, so that's what I mean. So there have been many, many theories of dark matter that have been proposed over the years, and we've tested them out, and all of them give us null results. So this is again an important thing. It is important to also publish your null results, so we know a lot about what dark matter is not. So yeah, so once you know that your theory is false, you can actually reverse the argument, and you can rule out certain kinds of theories. Okay, so if you have certain parameters of your theories, you can use this argument to say that certain parameters have been ruled out. So this is a particular theory of dark matter that people have proposed. So this is a dark matter that interacts with quarks via a resonance. So the way it would work is that you have two quarks from the two protons that collide, they form a resonance, and then it decays into dark matter. Okay, you can try to see it with the LHC, but you can also do an interesting thing is you can sort of chop this diagram in half and invert it. So if this resonance interacts with quarks, then not only can it be produced from quarks, but it will also decay back into quarks. And you can look at that as well. And so people have produced very complicated plots for this, but I'm going to simplify it for you. So what this plot shows is on the y-axis, you have the interaction cross-section, and on the x-axis, you have the mass of the dark matter particle. Okay, and the curved line is from direct detection, which means you just put a detector on Earth, and as it moves around the sun, you expect that it will hit some dark matter particles. And if it doesn't see anything, then you can put a limit on how much dark matter at most is there. So that is the limit that you see in the curved line. And the line at the bottom is the limit that you get from the LHC. So the LHC can sometimes see, for example, for this particular theory, can see much, much better than this direct search experiment. Okay. And then this was the second part of what I talked about. If it can go again back into quarks, then rather for looking for missing energy, you can just look at two quarks, or rather two jets, like I showed you before. And then you can see that the standard model prediction has been calculated for 7 orders of magnitude. So on the y-axis, you have things that go from 10 to the minus 2 all the way down to 10 to the minus 5. And we have precise measurements for all this entire range. So that means if you have one event of the kind at the bottom right, that means you have 1 crore events of the kind of the top left. Okay, and so we have these very, very precise measurements of the energy of two jets, and we can use that to rule out all kinds of resonances. Okay, so this is again a huge success of the LHC. So people, especially newspapers, only try to focus on what has been discovered. But to tell you the truth, we have a lot of experiments going on that do a lot of really precise measurements at energies that we have never done before. So the LHC and a lot of these experiments are doing a lot of new physics and new energy regimes that we've not seen before. And it only tells us how successful our current theories are. So that's something to remember, and that's something to be proud of as well. Okay. So the second kind of detection experiment is the direct detection experiment that I was telling you about, where you place a detector on Earth and you wait for dark matter particles to hit it. So this is the Xenon 1 ton detector, which is in Italy. And you can see there is a giant water tank, and there is a poster of what is in the tank on the tank. Okay, so that's what this picture is. The scale gives you how big the tank is, so it's 3 floors large. And what this experiment does is it has a lot of liquid xenon in it, and the minute a dark matter particle hits it, it will displace this xenon nucleus, and you have some ionization and some scintillation signal. That means light signal gets generated, and there are photomultiplier tubes at the bottom and the top that detect this light. And then based on how fast which array detected the light, you can actually pinpoint where exactly the collision occurred. So it uses this kind of apparatus to see to look for these invisible dark matter particles. And just 2 days ago, it had this very exciting result, which showed that they see more events than what they predict. Okay, so on the x-axis again, you have the energy of the recoil of this guy, and on the y-axis you have the number of events with that particular energy. And you can see at the top you have these two observations which don't match at all with what they expect. So what they expect is the red line, and then you have these two signal points where they don't understand. So this is very exciting, and people have already started writing new theories and making all kinds of predictions for this. So this is something new that is happening. So what will happen next for this? So the experimentalists will keep on taking more data. They have to make sure that this is not a statistical fluctuation or a fluke. They will test their model background very, very well. So because this is in a real experiment, you have to take into account all kinds of contaminations. You have to make sure that you've modeled all your materials really well and so on. So they will do all of that. While they are doing that, what theorists will do is they will think of new models that can explain behavior like this. What could cause an energy recoil of this particular size and nowhere else? Okay, so they will think of this. They will write down their theories, and there are many other experiments that are ongoing and have been conducted. So they will make sure that the theory that they write is such that it will be visible only in this and invisible everywhere else, because otherwise it would have been seen somewhere else. And not only that, the next thing to do would be to find new cross checks so this is a prediction. So if you write down a theory, you will also make a prediction of where else can you check whether this is true or not. And so putting all this together, hopefully we'll have some very exciting few years ahead of us. So this is what I'm showing you now is the LHC running plan. So you can see that it's going to run for a long time, well into the 2030s. And on the top you see is an axis where I show you the kind of energy you need to produce different kinds of particles. So it's in electron volts because that's the standard unit used by particle physicists. And the photon and the gluon have zero mass, so they are right off the scale there. And the electron and the quarks are at about 1 million electron volts. The top is the heaviest quark we know and the heaviest particle which we know, which is at about 175 billion electron volts. The LHC is twice that, 100 times that number. So we can produce a lot of top quarks at the LHC. And maybe people are thinking that there could be another 100 TeV collider in the future. So we can study even more new particles if they exist. So yeah, so let me end here. I'm sorry for being a little bit late. Yeah, so the summary is that the standard model has been arrived at after a lot of experimentation and testing many competing theories, but we still have many unanswered questions. And currently there are already 2,000 results already published by the LHC machine, and it is going to run for another 15 or 20 years. So we can expect many, many more things from it. Okay, I'll end here. Thank you. And if there are any more questions. Okay, where are we on right-handed neutrinos? Do we have any method to detect them? There are lots of theories and lots of predictions for how to detect them. There is no one theory. The simplest right-handed neutrino that you can write is pretty much useless because it doesn't interact with anything else. Yeah, it's not a very useful theory. But you can write right-handed neutrinos with more complicated models that do interact with the rest of the standard model somehow. And then depending on how they interact with the standard model, you can design how to detect them. There are lots of experiments for that already and lots of limits as well. Why is liquid xenon particularly used in the xenon quantum experiment? Apparently, xenon is a very, very good material for these kinds of detectors. So first of all, xenon is a noble gas, so it does not react chemically, which is very good. So once you have xenon, it's going to stay xenon. And it also has certain nice properties of scintillation and ionization that can give you very nice signals. So it's a very nice balance between how expensive it is to extract xenon and how much sensitivity you can get out of it. So you need a lot of xenon for these kind of experiments. So it's super expensive, but it also gives you a lot of really precise sensitivity. Okay. Dark matter, antimatter matter, etc. Is there any other N2 types of matter? They are not types of matter. The matter is just matter. Yeah, you should not think of it as different kinds of matter. It's like saying, I don't know. It's like saying you have mango, banana, apple. Is there any N2 kind of fruit? It does not make any sense. You can always make more distinctions if you want, and you can always call things by different names. Yeah, in my opinion, there is no such thing as it's not a different kind of matter. It's just different properties of matter. So antimatter is just matter, but it has certain mirror properties you can think of. That's all. Dark matter is also matter. It's just not visible to light, which is why we call it dark matter. It is not some different matter. It's just matter. Any more questions? Okay, so I think we can end here. I'm sorry, we were running quite late, but hopefully because we took questions during the talk and not all towards the end.
Thank you so much for sharing your knowledge, ma'am. And I'm sure everybody found it really interactive as well. I'm sure everybody gained a lot of perspective towards dark matter and particle physics and have more curiosity and more questions about it. Thank you so much for giving your time here for this talk. And to all our viewers, thank you so much for watching.